not to be confused with a fixed point where x equals f. In mathematics, particularly in calculus, a stationary point or critical point of a differentiable function of one variable is a point of the domain of the function where the derivative is 0. It is a point where the function stops increasing or decreasing. For a differentiable function of several variables, a stationary point is an input where all the partial derivatives are 0. The stationary points are easy to visualize on the graph of a function of one variable. They correspond to the points on the graph where the tangent is horizontal. For function of two variables, they correspond to the points on the graph where the tangent plane is parallel to the xy plane. Stationary points, critical points and turning points. The term stationary point of a function may be confused with critical point for a given projection of the graph of the function. Critical point is more general. A stationary point of a function corresponds to a critical point of its graph for the projection parallel to the x-axis. On the other hand, the critical points of the graph for the projection parallel to the y-axis are the points where the derivative is not defined. It follows that some authors call critical point the critical points for any of these projections. A turning point is a point at which the derivative changes sign. A turning point may be either a relative maximum or a relative minimum. If the function is differentiable, then a turning point is a stationary point. However, not all stationary points are turning points. If the function is twice differentiable, the stationary points that are not turning points are horizontal inflection points. For example, the function has a stationary point at x equals 0, which is also an inflection point, but is not a turning point. Classification. Isolated stationary points of a real-valued function are classified into four kinds by the first derivative test. A local minimum is one where the derivative of the function changes from negative to positive. A local maximum is one where the derivative of the function changes from positive to negative. A rising point of inflection is one where the derivative of the function is positive on both sides of the stationary point. Such a point marks a change in concavity. A falling point of inflection is one where the derivative of the function is negative on both sides of the stationary point. Such a point marks a change in concavity. The first two options are collectively known as local extrema. Similarly, a point that is either a global maximum or a global minimum is called a global extremum. The last two options, stationary points that are not local extremum, are known as saddle points. By Fermat's theorem, global extrema must occur on the boundary or at stationary points. Curve sketching. Determining the position and nature of stationary points aids in curve sketching of differentiable functions. Solving the equation f equals 0 returns the x-coordinates of all stationary points. The y-coordinates are trivially the function values at those x-coordinates. The specific nature of a stationary point at x can in some cases be determined by examining the second derivative f. If f less than 0, the stationary point at x is concave down, a maximal extremum. If f greater than 0, the stationary point at x is concave up, a minimal extremum. If f equals 0, the nature of the stationary point must be determined by way of other means, often by noting a sign change or around that point. A more straightforward way of determining the nature of a stationary point is by examining the function values between the stationary points. A simple example of a point of inflection is the function f equals x3. There is a clear change of concavity about the point x equals 0, and we can prove this by means of calculus. The second derivative of f is the everywhere continuous 6x, and at x equals 0, f equals 0, and the sign changes about this point. So x equals 0 is a point of inflection. More generally, the stationary points of a real-valued function are those points x0 where the derivative in every direction equals 0, or equivalently, the gradient is 0. Example: for the function f equals x4 we have f equals 0 and f equals 0. Even though f equals 0, this point is not not her point of inflection. The reason is that the sign of f changes from negative to positive. For the function f equals sin, we have f0 and f equals 0. But this is not a stationary point, rather it is a point of inflection. This is because the concavity changes from concave downwards to concave upwards and the sign of f does not change, it stays positive. For the function f equals x3, we have f equals 0 and f equals 0. This is both a stationary point and a point of inflection. This is because the concavity changes from concave downwards to concave upwards and the sign of f does not change, it stays positive.